Acceleration is a fundamental concept in physics that explains how an object's velocity changes over time. In this simulation, we explore an interesting case where an object moves in one direction while accelerating in another. This is crucial in understanding motion, forces, and the effects of gravity. By examining the motion of a lightweight rocket with a powerful engine, we can gain insight into the relationship between force, acceleration, and velocity. To begin, we set the rocket's mass to 0.2 kilograms with a burn time of 1.5 seconds and a thrust of 10 newtons. These parameters ensure that the rocket accelerates quickly and for an extended period. The simulation demonstrates how the rocket initially moves upwards due to the strong force of its engine, but later experiences a reversal in acceleration once the engine shuts off. This transition provides valuable information about how objects behave when subject to different forces over time. Initial acceleration, the upward motion. When the rocket's engine ignites, it generates an upward force that propels the rocket into the air. At the same time, gravity acts downward, opposing the motion. Despite this opposing force, the thrust from the engine is significantly greater, allowing the rocket to gain speed rapidly. During the first 1.5 seconds, the rocket's velocity increases dramatically, reaching a little over 60 meters per second by the time the engine cuts off. By observing the velocity versus time graph, we can see how quickly the rocket accelerates. The slope of this graph represents the acceleration, which remains constant during the burn phase. Because the engine provides a strong and consistent thrust, the rocket gains speed at a steady rate. This period of rapid acceleration highlights how external forces influence motion when there are no other significant resistances, such as air friction, in play. The high acceleration experienced by the rocket can also be described in terms of g-forces. A g-force is a measure of acceleration relative to Earth's gravity. In this case, the rocket experiences about 4 times the acceleration due to gravity. This level of acceleration is significant, as it demonstrates how powerful forces can rapidly change an object's motion. Transition phase. The engine cuts off. At exactly 1.5 seconds, the engine stops producing thrust. However, this does not mean that the rocket stops moving. Because it has built up considerable velocity, it continues to rise for a significant period. The only force acting on it at this point is gravity, which applies a steady downward pull. Without any additional upward force, the rocket's velocity starts decreasing. Although it is still moving upward, it is no longer accelerating in that direction. Instead, it is decelerating, meaning its upward motion is gradually slowing down. The velocity graph clearly shows this change, as the steep upward slope becomes shallower after the engine shuts off. This phase is crucial in understanding how acceleration and velocity interact. While many people associate acceleration with an increase in speed, it is important to recognize that acceleration can also slow an object down if it acts in the opposite direction of motion. In this case, gravity serves as a negative acceleration, reducing the rocket's velocity until it eventually comes to a stop. Reaching the peak, motion stops temporarily, since the rocket was moving at around 60 meters per second when the engine cut off. It takes time for gravity to bring it to a complete stop. During this period, the velocity steadily decreases. Based on the effects of gravitational acceleration, we can predict that the rocket will take a little over 6 seconds to reach a velocity of 0. At this exact moment, the rocket reaches its highest point. Here, its velocity is 0, meaning that for an instant, it is neither moving up nor down. However, this does not last, because gravity continues to act on the rocket, pulling it back down toward the ground. The descent, falling back to Earth. Once the rocket reaches its peak, it begins its downward journey. gravity remains the only acting force, meaning that the rocket now accelerates downward at a constant rate. The motion here mirrors the earlier phase, where gravity was slowing the rocket down, except now it is speeding it up. The velocity graph now takes on a steep downward slope. The descent occurs at the same rate as the previous deceleration, meaning that it will take roughly another 6 seconds for the rocket to return to its original launch height. By the time it reaches the ground, it will be traveling at the same speed it had just before reaching its highest point, only now in the opposite direction. The position versus time graph provides further insights into the motion. Initially, as the rocket is accelerating, the graph curves upward. Once the engine shuts off and the rocket begins slowing down, the graph starts leveling out. At the peak, the position graph is at its highest point. When the rocket begins its descent, the curve starts heading downward, representing its return to the ground. Exploring different scenarios. One of the greatest benefits of this simulation is that it allows us to explore different conditions and observe how acceleration behaves under various circumstances. Some key variations include a heavier rocket with the same thrust. If we increase the rocket's mass while keeping the thrust constant, the acceleration will be lower. This means the rocket will take longer to reach high speeds, and it may not reach as great a height before gravity slows it down. A rocket with a longer burn time. Extending the burn time allows the rocket to continue accelerating for a longer period. This results in a much higher final velocity and a significantly increased peak altitude. A rocket with less thrust. Reducing the thrust means the rocket may struggle to overcome gravity. If the thrust is lower than the gravitational force, the rocket will never leave the ground. The effect of air resistance. If air resistance is included, the rocket's motion changes. It will take longer to accelerate, and its peak altitude will be lower. Additionally, its descent will be slower, as air resistance counteracts gravity. Conclusion: this simulation provides a valuable demonstration of how acceleration influences motion, particularly when an object moves in one direction while accelerating in another. Through the example of a rocket launch, we observe the effects of thrust, gravity, velocity, and acceleration over different phases of motion. The ability to analyze velocity versus time and position versus time graphs enhances our understanding of motion and acceleration. Additionally, the flexibility to modify conditions in the simulation allows students and learners to explore real-world applications of physics principles. Understanding acceleration in this way is crucial in fields such as aerospace engineering, physics, and mechanical design. By grasping these concepts, we can better predict, analyze, and apply motion dynamics in various scientific and technological advancements. This simulation not only clarifies a fundamental principle in physics, but also encourages curiosity and experimentation, making learning a more engaging and interactive experience.